are single elemental semiconductors. They belong to the fourth group of the modern periodic table of elements. Silicon and germanium are the most commonly used elemental semiconductors. Compound semiconductors are formed by using two or more elements. They are synthesized using elements from groups 2 through 6 of the periodic table. Compound semiconductors may be further divided into different types, such as inorganic compounds like cadmium sulfide, gallium arsenide, cadmium selenide, etc., and organic compounds like anthracene, doped phthalocyanine, etc., and organic polymers like polypyrrole, polyaniline, polythiophene, etc.
A semiconductor, without any artificially added impurity, is called an intrinsic semiconductor.
Both silicon and germanium, the two most commonly used semiconductors, exist as intrinsic semiconductors. Let us take a look at the atomic structure of silicon and germanium. Both silicon and germanium have 4 valence electrons. In crystalline form, each silicon and germanium atom uses its valence electrons to form 4 covalent bonds with 4 surrounding atoms. Let us use the crystal structure of silicon to further study intrinsic semiconductors. Remember, the following discussion applies equally to germanium in its intrinsic form. At absolute zero, all the covalent bonds in the crystal lattice of an intrinsic semiconductor are intact. Thus, at absolute zero, there are no free electrons to occupy the conduction band, and the intrinsic semiconductor behaves like an insulator. However, at higher temperatures, some electrons gain enough thermal energy to break free of the covalent bonds in the crystal lattice. These free electrons move to the conduction band, and the material starts behaving like a semiconductor. Note that each electron that moves to the conduction band leaves behind a vacancy in the valence band. This can be visualized as breaking of a covalent bond, where an electron becomes free and leaves behind a vacancy in the covalent bond. An electron breaking away from a covalent bond takes away a unit negative charge with it, leaving behind a vacancy with an assumed unit positive charge. A vacancy with a unit positive charge in a covalent bond between atoms of a semiconductor is called a hole. Thus, whenever a covalent bond is broken in an intrinsic semiconductor, a free electron and a hole is created. We refer to this as an electron-hole pair. Hence, in an intrinsic semiconductor, the number of free electrons is always equal to the number of holes at any given moment. Consider a hole or a vacancy at position 1 in the crystal lattice of a semiconductor. Now, an electron from position 2 can jump to occupy the vacancy at position 1. This fills the vacancy at position 1 but creates a vacancy or a hole at position 2. Similarly, an electron from position 3 can jump to occupy the vacancy at position 2. This fills the vacancy at position 2 but creates a vacancy or a hole at position 3. As a result of such jumps of electrons across covalent bonds, the holes or vacancies appear to move across the crystal lattice of a semiconductor. Note that the movement of holes occurs because of the movement of electrons across covalent bonds in a semiconductor, and not because of the movement of free electrons. Thus, there are two types of moving charge carriers in the crystal lattice of a semiconductor: the negatively charged free electrons and the positively charged holes. When an electric field is applied across a semiconductor by connecting it across the terminals of a battery, the free electrons move towards the end connected to the positive terminal and generate an electron current denoted by IE. The holes shift towards the end connected to the negative terminal and generate a hole current denoted by IH. The total current flowing through the semiconductor is equal to the sum of the electron current and the hole current. If a free electron collides with a hole, it fills the vacancy in the covalent bond without the generation of any other hole. This is called the process of recombination. Under thermal equilibrium, the rate of generation of free electrons and holes in a semiconductor is equal to the rate of their recombination, so that the density of charge carriers in a semiconductor remains constant. As we learnt earlier, a pure semiconductor without any impurities in it is called an intrinsic semiconductor. Both silicon and germanium exist as intrinsic semiconductors. There are two types of charge carriers in the crystal lattice of an intrinsic semiconductor: the negatively charged free electrons and the positively charged holes. The conductivity of an intrinsic semiconductor increases with rise in temperature, as more number of electrons break away from the covalent bonds of the semiconductor atoms. However, at room temperature, intrinsic semiconductors have very low electrical conductivity. The electrical conductivity of an intrinsic semiconductor can be improved by increasing the number of free electrons or holes in it at room temperature. When a small amount of suitable impurity, say a few parts per million, is added to an intrinsic semiconductor, its conductivity increases to a large extent. A semiconductor that has an added impurity to increase its electrical conductivity is called an extrinsic semiconductor. The process of adding the suitable impurity to a semiconductor is called doping. Thus, an extrinsic semiconductor is also called a doped semiconductor. The impurity atom added to a semiconductor to increase its electrical conductivity is called a dopant. During the process of doping, the dopant gets positioned in the crystal lattice of the semiconductor. It is important that a dopant does not distort the crystal lattice of a semiconductor. For this, the dopant atoms of the semiconductor crystal should be comparable to the semiconductor atoms in size. We have learned that both silicon and germanium are tetravalent. That is, each of their atoms has 4 valence electrons. Commonly used dopants are either trivalent or pentavalent neighbors of silicon and germanium in the periodic table. Commonly used trivalent dopants that have 3 valence electrons are boron, aluminium, and indium. Commonly used pentavalent dopants that have 5 valence electrons are phosphorus, arsenic, and antimony. The addition of trivalent and pentavalent dopants creates 2 different types of extrinsic semiconductors. We know that in crystalline form, each silicon and germanium atom forms 4 covalent bonds with 4 surrounding atoms. When a trivalent dopant, say an aluminium atom, is added to a silicon semiconductor crystal, the aluminium atom occupies the same position of a silicon atom in the crystal. A trivalent dopant atom forms covalent bonds with 3 neighboring semiconductor atoms. However, the dopant atom has no electron to share with the 4th neighboring semiconductor atom. Thus, a vacancy or hole is created in the lattice. Each trivalent dopant atom creates 1 hole in the crystal lattice of the semiconductor. At room temperature, some of the electrons break away from their bonds, giving rise to electron-hole pairs. Simultaneously, some of the free electrons recombine with the holes and reduce the number Ni of intrinsically generated electrons to Ne. Thus, the number of holes in a semiconductor doped with a trivalent dopant is much larger than the number of free electrons in it. We learnt earlier that a positive charge is assumed to be associated with holes. Thus, positively charged holes act as majority charge carriers in a semiconductor doped with a trivalent dopant. Thus, such extrinsic semiconductors are called p-type semiconductors. In spite of having the number of holes NH greater than the number of free electrons Ne, the p-type semiconductor crystal remains neutral. As the charge of the additional charge carriers is equal and opposite to that of the ionized cores in the lattice. The movement of holes as charge carriers occurs when valence electrons from neighboring semiconductor atoms jump to fill the holes created by dopant atoms in p-type semiconductors. When a valence electron fills the hole generated by a dopant atom, the dopant atom becomes negatively charged. Thus, a dopant atom in a p-type semiconductor is called a negatively charged core or an acceptor impurity. A p-type semiconductor has an acceptor impurity energy band that lies just above the valence band. Thus, the free electrons can leave the valence band by covering a much smaller energy gap as compared to an intrinsic semiconductor. Valence electrons in p-type semiconductor can move from the valence band to the acceptor impurity energy band even at room temperature to create holes in the lattice. Thus, electrical conductivity of a p-type semiconductor is much better than an intrinsic semiconductor. Now let us see what happens when a pentavalent dopant, say a phosphorus atom, is added to an intrinsic silicon semiconductor crystal lattice. A pentavalent dopant atom in the crystal lattice of the semiconductor forms covalent bonds with 4 neighboring atoms of the semiconductor. The pentavalent dopant atom still has one very loosely bound valence electron that can be set free using a very small amount of energy. Thus, each pentavalent dopant atom contributes a free electron to the crystal lattice of the semiconductor. Therefore, the number of free electrons that are available for conduction by dopant atoms depend largely on the level of doping. If the doping level is high, the number of free electrons contributed for conduction by the dopant increases. This number of free electrons contributed by the donor dopants is not dependent on the temperature of the semiconductor crystal. On the other hand, if the temperature of the crystal is raised, the number of intrinsic electron-hole pairs increase, and this further adds to the conductivity of the crystal. Hence, in a semiconductor doped with pentavalent dopants, the total number of conduction electrons, Ne, is due to the free electrons contributed by the donor atoms, which are pentavalent dopants and those generated intrinsically. But the total number of holes, NH, is only due to the holes from the intrinsic source. Due to the increase in the number of free electrons, the rate of recombination of holes increases. This gives rise to a reduction in the number of holes effectively as compared to the number of free electrons available for conduction. Thus, the number of free electrons in a semiconductor doped with a pentavalent dopant is much larger than the number of intrinsic holes. Negatively charged free electrons act as majority charge carriers in a semiconductor doped with a pentavalent dopant. Thus, such extrinsic semiconductors are called N-type semiconductors. When a dopant atom in an N-type semiconductor gives up a valence electron, it becomes positively charged. Thus, a dopant atom in an N-type semiconductor is called a positively charged core or donor impurity. A N-type semiconductor has a donor impurity energy band that lies just below the conduction band. Thus, electrons can jump to the conduction band by covering a smaller energy gap as compared to an intrinsic semiconductor. Free electrons released by donor impurity atoms in an N-type semiconductor can move from the donor impurity energy band to conduction band even at room temperature. For example, the energy required for an electron to jump from valence band to conduction band in an intrinsic silicon semiconductor is about 1.1 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.05 electron volt approximately. Similarly, if the semiconductor crystal is made of germanium, the energy required for an electron to jump from valence band to conduction band is about 0.72 electron volt. If it is doped with a pentavalent impurity to a suitable level and converted to an N-type semiconductor, the energy required for an electron to jump from the valence band to conduction band reduces to 0.01 electron volt approximately. Thus, electrical conductivity of an N-type semiconductor is much better than an intrinsic semiconductor. It can be shown that at thermal equilibrium, Ne into Nh is equal to Ni square. Here, Ne, Nh and Ni denote the concentration of electrons, holes, and intrinsic carriers respectively. You will learn about the details of the equation at higher classes.
दोस्तों, यदि आज की वीडियो आपको अच्छी लगी हो तो लाइक कीजिए, चैनल को सब्सक्राइब कीजिए और अपने दोस्तों के पास इस वीडियो को शेयर कीजिए। अगर आपका कोई कमेंट हो तो कमेंट बॉक्स में नीचे जरूर लिखिए। थैंक यू।